So on this one, we're going to do, what is this? Wait, 3.83. Okay, yeah. So this is max power can be extracted by the load resistor. So what we do with these kind of problems, these are looking at a larger circuit, and it's going to ask, like, what's the max power by one resistor? So we're going to use what we've learned from Norton and Theremin circuits to be able to simplify this half of the circuit into a single power supply. So they're saying they didn't give us one, so we're going to use Norton circuit then, or Theremin. It doesn't matter, to be able to determine what this is. So we'll have a single resistor. If we use Theremin, we'll have a resistor in series with a power source in series with the resistor, and that's going to tell us what's coming into this one. So that way we can calculate the power coming through there. So there's a couple different ways to do it, but we're going to use this Theremin method for this one because it's a nice way to show the method in practice. So first thing we do is we choose which method. So we're going to do a find Theremin. And so with any of the Theremin ones, as we know, we have to do a power supply, and we're going to have a resistor and an open, and a resistor and an open. And that way, once we get to here, we'll know what this power is, what this what this voltage source is, what this resistor is, and then we'll be able to just put another resistor in there and calculate it out nice and easy. So first bit, find the Theremin equivalent circuit. And we do that with by looking here. So first thing that we're going to do is I'm going to write this as V1, and we're going to break this off there. So we're going to chunk that away, ignore everything on that side of the page, have it two open hanging things right now. And to calculate what V1 is, we're going to use a voltage divider. Because right now, if this is open, we only have power current coming through here and current going down. We don't have anything over there. So this is just a very standard voltage divider circuit. Remember, we've got bum, bum, bum. So remember, this is our voltage divider circuit, and we're taking the voltage that comes out in between any two of these. So this is going to divide the voltage from whatever that is. So if this is 10 volts, and we got 5 and 5, we're going to be able to divide it that way. Anyway, so voltage divider circuit, we're going to get V1 equals R2 over R1 plus R2V. That's our normal voltage divider equation. So that's going to be our R2, and our R2 is going to be 6 over 3 plus 6. And where do we get that? 3 plus 6, 6 over 3 plus 6, times our source voltage, which is 15. Cool. And that's going to be 15 times 6 over 9, 2/3, 15, 5, 5, 10, right? 10 volts. 10 volts, okay. And that is our first one. So, our next bit we're going to solve for is what is our Ix? And our Ix is going to be equal to what? Well, we've got V1 to 0, so V1 minus 0 over 6. So that's going to be V1 over 6. And we just found what V1 is because we did the voltage divider. We did 10, so that's going to be 10 divided by 6. And that is our Ix. That's going to be in milliamps. Okay? 10 divided by 6 equals Ix equals V1. Cool. All right, so now that we found that, we are going to start checking out what's happening up here with our dependent source. So, dependent source. So, for this, we've got 2000 Ix equals, well, our Ix we just found over here, so we're going to plug that in there. So it's going to be 2000 times 10 over 6 is going to be equal to 3333. Remember, we have powers of 3, 1, 2, 3, 10 to the minus third. So that's going to be that volts. Boom. Our dependent, and remember, it's a voltage source, plus and minus, so we have volts coming out, not amps. Just as a quick thing. So 3.3 volts is what's coming out. So, since we've cut this circuit open, there's no current flowing through here. Remember, everything on this line is the same because no current flows through. We've had this many times now. So, now what we're going to do is we're going to do something. We're going to close the circuit. Do we want to close it first? No, we want to calculate something out first. So, when we have it open, like we do right now, we have VTH, the voltage, the Theravin voltage, equals V1 minus 2000 IX. And we already saw for that one. We saw for that one equals 10 minus 3.333 equals 6.67. I'm going to simplify it. Equals V Theravin. Cool. Cool. So now we're going to close the circuit. So now we're going to draw a fake little line in there. And we're going to call this ISC. And we're going to draw a line coming down because it's the current ISC. And now that we've done this, we have two neat little things inside of here that you should see quickly to be able to calculate. We have I1 and we have I2. So we should be able to calculate this nice and quickly through this. So let's try it. So put a line there. This is to close the circuit. So in order to solve what I1 is, I2 is, and that's going to give us what ISC is, of course. So we're going to go around the loops. So I1, we have 3 and 6, so we're going to put I1 down. We're going to have our 3 plus 6. Cool, cool. We're going to have our minus I2, and that's going to be the shared one, which is 6 equals 15. Nice. That's our first equation. Our second equation is going to be for I2. We're just going to put I2 down. And now our I2 is going to be 4 and 6 equals 10. And then minus I1, which is the shared 6. And then we are going to have our voltage source, which is 2000 IX. Okay, so that's our second equation. I'm going to hold it there. And now we're going to look at what is IX. Well, let's look. IX right here is going down through these, so it's the difference between these two, and it's going in the direction of I1, which gives you which way is positive, which one's negative. So IX equals I1 minus I2. Because remember, it's going in the positive direction, same as I1. I1's the positive, this is the negative. Okay, because it's the one in between. So we have our three equations, three unknowns. So we solve these now. We're going to do 9 minus 6, 0, minus 6, 10, 2, 1, minus 1, minus 1. Okay, and then we're going to get 15, 0, and 0. Alright, and that's going to be here. So let's just check. We see how we got that coming from here. 9 minus 6, 0, 15, minus 6, 10, 2. Remember, this is, you have to do your units. This is a units thing. You got to bring it down to normal units that match the other ones. So 2. And the last one, 1, minus 1. If we pull this over, that's minus 1, then we get there 2. So let's plug that into the calculator. And we're going to get 2.5, 1.25, 1.25. I1, I2, IX. Excellent. Can we see that? Oh no, we didn't write any of that. Well, sorry guys, you'll see it now. Just run through. We did all that. We put it in our thing. We put it in the calculator. Okay. So now that we have our I1, our I2, and our IX, we're going to do our resistor Theravin, and that's going to be equals V over I. Resistance equals V equals IR, so the I's pulled down. And that's going to be our 6.67, which we calculated over here. That's our resistance of Theravin, so we can even put resistance Theravin there, over our I. And that's going to be 1.25, and that's going to come out to 5.3. Pretty sure. Let me try that one more time. 6.67 divided by 1.25. Yeah, 5.3. Cool. And that equals our R Theravin. Cool. And this is also going to equal what our max power is, right? Because this is going to be this entire piece that's going to be useful for max power. That's the resistor that the max power has over there. So we've simplified all of this. So that's how much the circuit is sucking up. So we have that. Now we're going to go for I. And the I, V equals IR, is 6.67 over 2 times 5.3 equals 0.625 milliamps, of course. Okay, then we just grab that from putting this in on the bottom. We've got our 6.67 on the top. This one we've got our 2. And then finally we've got our power equals I squared R. And that, if we plug in our I squared, and then our R is going to equal 2.09 milliwatts. Wow, excuse me, milliwatts. So it's a tiny amount of power, small. But that's how you solve this kind of one. Let me know if you guys have questions at all, and we can go back through it. All right.